Steve, all right, everyone. It's the last talk of the day, certainly not least. We got Steve here from Hortonworks, who's going to be talking about Spark and object stores.
Hi, everyone. I'm Steve Loughran. I like to view myself as the person in the middle of your stack traces. Hands up who's ever seen a stack trace in Java or Spark? Anyone there? Yeah, okay. That's me. Also, we've got hands up. I'm talking about Spark and object stores, but hopefully this may actually be relevant to people. So hands up if you're using Spark in cloud of any form. Right, hands up for Amazon, the big one. Azure, anyone out there using Azure? 2 people. Anyone at all using Google Cloud? Okay, 2 people. Right, I'm going to cover Amazon mostly, okay, because it is the big one. I'll try and be fast. I will try and not hold you up before beverages. So I've been working about the past year very much on improving how the whole Hadoop stack works with object stores. And there's 3 main deployment use cases that we encounter and we've been dealing with. Okay, and this is to put things in context. Hopefully you're working the same way. So big use case, the classic one is some form of long-lived cluster doing some kind of batch work. ETL is an example where your logs are coming in, they're being stuck on one S3 bucket, something like that. You bring up a cluster for a few hours a night, something like that, do your batch analysis, stick it back in the proper format. You've got it out of CSV, you've stuck it into something like Oracle Parquet. Now you can properly process it. Here you've got a short-lived Hadoop cluster, HDFS for your storage. If you want to spend lots of money, you can have a long-lived Spark cluster, in which case you get to pay Amazon for all your EBS storage. If you're going to have something short-lived, you need to keep your data on object stores, and that's what this does. Next big use case, notebooks. This is where Amazon and things are really good fun for, and you can just spin up a notebook fast. Apache Zeppelin being the standard Apache one. You can keep your data, they actually persist it to the object store, like Amazon S3. And then you do your work with that data that was gathered earlier on. Advantage here is that you can bring up short-lived clusters for the lifespan of your team. You can also isolate security-wise so that your data scientists, they only have the cluster with the permissions of their particular team, that particular group. The rest of your data is all kept nicely hidden and out of sight. There is another nice little advantage that doesn't get discussed, which is your project can bring up the version of Spark you want, and you don't have arguments with anybody else in production about which version of any particular library they have. That makes you very flexible in production, so it's worth bearing in mind. And the most cutting edge use case of all, and I'd be really curious if people are getting away with this in production, is actually Spark streaming on a cloud environment. Is anyone in the room doing that? 1 person at the end. Okay, 2, 3, okay, well done. Does it work reliably? Yeah, shakes the head. Here, this illustration I've actually shown Azure being underneath it all, and that's because this thing does work on Azure because it's slightly different from Amazon. I think we can do more here to make things better. Now, why do things work and not work? The answer is because everything up the stack is built assuming we're working with a file system. We assume that data lives in files, and the files live in directories. Okay, it's nice and simple. In HDFS cluster, we have all the data living in the data nodes way off on the left, and we have a name node that actually just keeps the names of directories and files. And that's really cute because we can do transactions on that name node, like renaming a file, instantaneously, well, nearly instantaneously, save the result as a transaction, and it's nice and it just works. And that's important because rename is the standard way of committing work. At the end of any query, any operation, internally in Spark, when it commits stuff, rename is it. In contrast, object stores, they store objects, blobs. Again, they're farmed out over a massive cluster of machines with just hard disks. But this time, the choice of where those hard disks, which ones to use, is based on some hashing function applied to the full path. There's no notion of directories anymore. There's just objects with slashes in the names. means there's no single point of failure in a cluster, but it means to actually do a rename is gone. If we're trying to rename code, if you're trying to call rename from the Hadoop APIs in Spark, there's no rename taking place. There's a copy, then there's a delete. The time for that is as long as it takes to actually copy data around the storage array, and it can fail halfway through, in which case your system is in an undefined state. The other fun thing about object stores, we use REST APIs. Strength, it's portable. Other strength, you can actually use it by hand if you try hard. Weakness, it's horribly inefficient. We're setting up and tearing down HTTP connections, HTTPS connections, even worse. You're limited in what you can do, and it's very inefficient, especially for the list operations. There's usually some operation at the end for listing. It comes in blocks of about 1,000 at a time, and you have to keep repeating it till eventually you can list a big directory. Also, for bonus fun, this stuff is eventually consistent, meaning you can do something and it's not immediately visible. I can get an object, it's all there, nice and happy. I delete it, it's gone, and then immediately afterwards I can do a get and it's still there. People using Spark in EC2 may have encountered this and not even noticed. Well, you will have noticed, but you've not realized this is the cause. And the way it fails is you delete a directory before you start doing another query into that directory, and you get an error message saying, hey, there's something there, I can't do my work. Or sometimes the listing takes a while to catch up, so you create something, and then you try doing something with that data, and it's not there. The data has vanished, or it hasn't appeared yet. So things aren't quite the same, except for better or worse, they look the same, because there is one API that brings everything together, org Apache Hadoop FS file system. It's a class that lives in Hadoop, and it's just driven purely off URLs. Everyone has a URL to a path in the file system, which has something like HDFS in the front, or S3. That gets magically loaded with all its classes and dependencies, and then you work with it thinking it's a file system. As I've just tried to explain to you, it isn't. The code above doesn't realize that, though. There are lots of little file system drivers out there. HDFS is the main one. When you're working with object stores, Amazon themselves, for historical reasons, use a URL beginning with S3. Okay, so if you want EMR themselves, you must use that. Apache Hadoop, for a long time, we used something called S3N, since about 2009. And in 2015, we came up with a new one called S3A, which is the better one that you should be using. Why did we give it a different name? Because the new one uses the Amazon SDK, and even though we could have just replaced the old one in place, we stuck it in alongside because we didn't want to break things and have people really upset when we shipped something with bugs, which of course we did. But being open source, people found and fixed. So from now on, if you're talking to Amazon S3, use an S3A URL, okay? S3A, not S3N. Any bugs related to S3N will be ignored with the message, please upgrade to S3A. Anyway, getting these things working then, big problems, getting your class path right, getting your secrets in, working with it, and then dealing with that commitment problem. As I said before, if you're working with it, Amazon S3, and you're not on EMR, use S3A, okay? It's the one that I'd be working on. If you use this code, you will get the best, the fastest, and it'll be my code in the stack trace, I'm afraid to say. So, always the pain, getting that class path right. Step one, you want Hadoop AWS in there. You will want the matching AWS Java SDK in there. Amazon's SDKs have been very, very brittle against changing their signatures and versions, which means that you have to be absolutely in sync with the ones that we built the Hadoop jars with. I'm sorry about that. We're working with them to make things better, and they've been actually playing just about a week ago, released a fully shaded version of the Amazon SDK, which, if that's stable, that's going to be really good news. Otherwise, you should be getting everything that comes with Spark itself. Now, the official Apache distribution does not come with the AWS jars or the Azure jars. There is a patch out there, Spark 7481, which is actually, the pull request is how we in Hortonworks throw them all in. So you can download and build that yourself if you want. You could even add a suggestion to the Spark committer saying, please get this patch in. Otherwise, you're going to have to drag and drop the relevant jars into your Spark home/lib directory. Get the jars in, get your secrets in. The most important thing you have to remember with your credentials is do not give them away to anybody. Otherwise, not only do you lose access to all your data, you could have your data deleted by somebody malicious, and they will use your credentials to bring up Bitcoin mining VMs at spot prices around the world. In particular, do not ever commit these to any form of revision control, especially not Git, because you think you've deleted it and then updated it, but in fact the secret's still there. You can configure it in your Hadoop core site or your Spark config. You just set the access key and the secret key. We're now supporting session keys as well, which is far more secure, where you can just programmatically ask for a session key and use that for the lifespan of your application. Spark Submit is actually quite cute in that you set the environment variables and it will automatically copy them on. So if you're doing work from your laptop, set the environment variables and the secrets will make their way over. If you're running in VMs on EC2, you can ignore this slide completely because it's all done for you. When your VM is spun up, it will pick up secrets from Amazon saying you have the access rights to this role. What that means is in production is you should give different clusters, different roles, and set the permissions on all your buckets based on those roles of those VMs. When you try and do this, you will find your code probably doesn't work from time to time. As usual with anything security related, you will get no meaningful error message whatsoever. You will get a 403 or 401 and nothing useful. Generally, this means you've got your credentials wrong or you didn't even set them in the right place. But actually, there's a special fun one with Java 8 and the Joda time jar, which is that for some reason the Java 8 update stopped things working because Amazon doesn't know when your machine is anymore. It gets its time wrong. And if your clock's wrong, then Amazon won't trust you either. So that's the other really obscure problem is actually you've got a VM and it's just clock's drifted too much. So if all else fails, check your clocks. Now, once you've got all that done, life becomes simple. At least when you're reading, it's just another URL. Use the S3A prefix and it all works. This example, you can all type it in at home, it'll work because Amazon have a nice Landsat bucket we can read. And it just says, okay, read the 20 megabytes CSV file, and it'll just be read in. You can do that on your laptop, you can do it in production. The time to read your data is, of course, proportional to how far away you are. If you do it on your desktop, it's going to be slow. If you do it in the same cloud, same region as your actual bucket is, it's going to be a lot faster. If you unintentionally are running your code in some EC2 VMs on a different site from where your buckets are, one, it's going to be slow. Two, at the end of the month, you're going to get a larger bill for all the data you've read in. Hands up who's done that in the audience yet? Okay, I know, you're all denying that fact. Every so often it happens and people get upset. Whoever pays the bill gets upset. One of the tricks is to actually include the region in your bucket name. Okay, that stops you accidentally doing it. Anyway, it all just works, roughly, at least at read time. You can also write the stuff out as well. You can say, once you've read it in, you can say, right, I'm going to write it in a couple of places. It will generally work quite well in demos. Right? I'm not going to demo data. And that's the problem, is it generally works. It looks like it works. It goes, oh, it's done. I can do it. It's great. 2 points to catch out. One, because we're doing that copy rather than rename, it will take time proportional to how much of data you've created. So again, in a demo, small amount of data, it's nice and fast. Production, once you start writing out 100 gigabytes worth of data, it takes a long time. Similarly, once you start writing lots and lots of blobs in there, once you have many executors doing a query, there's more risk of a list inconsistency surfacing, and some of your data isn't copied over because it's not noticed it's there. Okay? Those are the things to look out for. Those are why, certainly in Hortonworks, right now we say you should not commit your work directly to S3. Right now, we say that. We say, bring up HDFS with the system, put your data in HDFS, and then before you tear the cluster down, the data you want to preserve, you copy to S3 then. Okay? Anyway, it's there. Reading ice does work. You can use all the data frames as well. Using the Amazon data sets, we can filter out all Landsat photos they have where there's a negative amount of cloud cover. And again, you'll find them. Because of the performance issues, if you are working with data on S3, you want to filter things as aggressively as you can. You want predicate pushdown. You want to declare up front which columns you want and select as few as you can. And again, if you want performance, just copy the stuff to HDFS, especially for things that you'd be reading lots of times. The problem with S3 is you've got limited bandwidth. The more executors hitting the same object, they're sharing bandwidth, disk I/O bandwidth, and your network traffic for talking to S3 is shared with all the other computation you're going on, as well as potentially noisy neighbors in a VM where something else is killing your bandwidth too. So copy to local HDFS for temporary stuff and you get better performance. Later on, if you look at these presentations online, you will get these settings and you will type them in your defaults. Just for now, it says turn on as much predicate pushdown as you can. That's the key thing. And so maximum efficiency on your predicate queries, least amount of metadata saving and summary stuff. I have some very good news here. In Hadoop 2.8, when we get it out the door, HTTP 2.5, and the next version of Cloudera, I suspect, we've done a lot of work in improving performance. In particular, we will say you set a read-ahead range, and instead of actually closing and reopening connections as you seek through a file, which is what we do right now, we can just say read-ahead 256K before we do the next, before we actually bother trying to seek. We also have a little flag there when you're working with Orc and Parquet to say use random I/O. It turns out, the normal way we read S3 is we do one big long get with a content range of where you start from your seek, all the way to the end. That is great for gzip files. It's absolutely great for CSV files. It's utterly atrocious for things like Orc and Parquet, where we're skipping forwards and sometimes even backwards. So when we say random I/O, we say just read in blocks, don't read past where you want, and we can then recycle HTTP connections. So it's way more efficient for bits where we're reading small blocks at a time. At the same time, it's pathologically bad for the big files, so we haven't made it a default. You're going to have to turn it on a case-by-case basis. I've also done some very nice work where we can stream output up to arbitrary large files as we go along, so you get better performance on the write pipeline too. So when this stuff ships, it'll be great to use. You can actually put it in your code configurations right now because it's harmless generally, so just start now anyway. Now, like I said, commitment is the enemy. You get random pauses at the end of work. It's particularly bad on S3. It's a lot better on Azure, actually. The key setting you're going to want is Spark, Hadoop, MapReduce, fileout committer, algorithm version 2. That cuts the number of renames down in half. It's still doing lots of renames, but it's doing them slightly earlier and there's less of them. Okay? So that's version 2. That doesn't make the problem go away. It certainly does not deal with the consistency problems, but it makes it faster. Now, at this point, people in the audience are probably whispering, saying, what about the direct committer, the secret direct committer? Which, if you don't know the history, Databricks wrote a committer that said, we will skip the renames, we will write into destination. Spark 1.6 actually stuck this in the code base and shipped it, the direct Parquet output committer. And Spark 2 pulled it out and refuses all bug requests, saying, please, it's gone, add it back. Because the problem is it couldn't handle failure. It basically says, the committer says, we do all our work into destination directory. As long as everything works, as long as every executor completes, all is well. If anything fails and gets restarted, no one knows what's already been written to that directory. There's no idea what happened, so you just don't know what's gone wrong. You also can't use speculative execution where you tell two executors to say work simultaneously, which has always been important on a physical cluster to deal with disks playing up. It's very important in a virtual world in case one of your neighbors is giving you bad performance talking to the object store or not. So speculation is nice. If you've ever tried it, if you turn speculation on and a committer with the word direct anywhere in its class name, Spark will tell you off and then ignore you. Okay, so I am writing a better committer, but I'm deliberately not using the word direct in its title purely for this reason. Now, Azure, I'll mention it is architecturally nice. It is a better substitute for HDFS. Microsoft do bill you a bit for that extra luxury. Okay, that's the price. Anyway, this time you want Hadoop Azure on the class path, you want Azure storage, plus some other miscellaneous jars that come free with Spark anyway. You have to get your credentials into your configuration. They are long binary things. You mustn't leak them, and there's nothing magic to environment variables, so stick them in your configuration, and it works. Again, if you bring up VMs in Azure, don't worry whoever's taking that photograph. That's not my real credentials, don't worry. No, I'm not that stupid, I hope. I'll run back and change them after the talk just to make sure. Anyway, so you could do that, and again, if you bring it up on VMs, it's all going to be magic. Now, one thing you can get away with Azure, because it's more like a real file system, is you can actually get away with streaming on it. And here you just say, right, I've got my Spark context, I've got a streaming context to poll regularly. Here is the URL of my object store to check, and set it off to do some work. A couple of things to know here, and this will actually work with S3 as well, at least as far as polling goes. The way Spark streaming works against an object store is it does a listing of everything that's in there, looks at files that have changed. Because listing is a performance killer on any of the object stores, the more files you've put in a directory, the longer and longer and longer it takes to poll for changes in a new window. So clean out the directory of any old cruft. You might say, right, every hour or so I delete old files. The other thing to consider is, again, the normal best practice for working with streaming is write to a directory near where the streaming directory is, and then finally commit it with a rename. The reason you need to do that when you're streaming to a file system is because Spark will see a file that's only been partially written and say, hey, here's a new file, hand it off to your streaming code, even though the file's not complete. When you do the write, close, rename strategy, it guarantees that only the completely written file gets picked up by streaming. In contrast, because the way object stores work, the object doesn't actually exist until the put's finished. So you can actually have your code say, I'm going to write streaming code straight into my destination directory and not bother with any rename. Okay, so that's the secret for performance there. But clean the directory out, and you're going to have a bigger window than you think. One thing to look out for also is checkpoints don't work, again, because they're using rename. So try to checkpoint less frequently than you think you need. Often you will find that actually more intermittent checkpoints is actually, you can just rebuild faster on the failway. You don't need to checkpoint quite so often. Anyway, I've been pretty depressing you right now, saying, oh, you're all doomed. The good news is there is some work going on between myself, a couple of people in Cloudera, and a couple of engineers from Western Digital to produce something better for talking to S3. The project name is Seaguard, Hadoop 13345, to give it its more technical title, where we're going to fix all of this, probably. Right, so the key point is that we are going to use Amazon's DynamoDB as that consistent metadata store where we get consistent directory listings, we get performance. So what happens here is every time I do a query, I'm going to hit DynamoDB first. I'll get an answer nice and fast. When I manipulate the file system, like deleting, I'll do it both in the real data and update the database. And I do a query, I'm going to get the consistent one because Dynamo is up to date. This is fast for metadata queries. It's fantastically fast for directory listings. And because it's now consistent, it means when I list a set of objects in a directory, I will get back exactly the objects that are there. That means we can start doing the next step of the code, which is my homework for the month. I'm partway through it right now, which is called, I would call it a direct committer, but of course we can't. So it's called a zero rename committer. And I'm not going to the details right now because it will scare people. But essentially, we're relying on the fact that on Amazon, you can write massive multi-gigabyte files, not in one single go, but as a step in intermediate parts. And at the end of the write, you say, here is the file, instantiate it. And normally we do that on a single machine during our write. This one actually delays committing the file until the end. So we should be able to have multiple tasks, multiple executors, all writing to the same destination directory. And only those tasks that we've finished will we actually commit into place. Like I said, it's a work in progress. All the code is in public. So when it's ready to play with, I would encourage people to do that. Right now, its status is core code is working. I'm working on the committer. We're going to have to think, we're going to do a lot of testing on this before we can trust it, because things are demo ready doesn't mean it's actually production ready. So, giving you a quick overview of what's happening. I've tried to scare you with a bit of the things you mustn't do, and I'm promising a future where things will be better. The key thing to know is they're just another file system URL. At least they look like that. To get them to work, you've got to get the class path correct. You've got to get your credentials on there. But you need to be aware it's not quite a real file system, and things will come back to hurt you. What might work quite nicely is your little sample test things. They can go horribly wrong in terms of either performance or actual consistent outcomes behavior. We've got some new options coming along that are going to really improve your performance, and that's both read time and write time. And when we get this CGuard thing together, it'll make your life good enough working with Amazon code that you should be able to use S3 as direct destination for both streaming and the output of any other Spark queries. So, at that point, are there any questions? Someone at the front there.
How much of that applies to Google Cloud Storage?
How much applies to Google Cloud Storage? Okay, Google Cloud Storage. GCS comes from Google. They have their own little jars which they produce. It's not on the Apache code base. The primary way so far that I've encountered, firstly, technically, it's more like Amazon in terms of its consistency, okay? Except that they also have, I think, an option where you pay a bit more, you get more of a consistent thing. I have a fundamental issue with GCS, which is they do not run the test suite that we in the Hadoop project provide so that people can test their file systems work with Hadoop. And I know that because they can't get Seek right. And basically, if you can't implement Seek, then I can't trust the rest of their code. And if you look, there are complaints from me on GitHub saying, why aren't you running our tests? You can't fix Seek. And they go, oh, we would like to do that, but we don't have time. So that's my issue with Google Cloud, is not whether it's better or worse, but how well it works with Hadoop for a product they're actually shipping, right? Sorry.
So I want to make the comparison to EMRFS and S3 DistCP. Are you taking design considerations from that?
Right. Amazon do a lot of work. They've essentially forked their stuff off a long time ago. We look at what they've done. We talk to them about things like SDKs and things like that. At least I talk to the Amazon SDK people, though the EMR team don't actually talk to anybody else. Well, I think it stops them being contaminated and sharing stuff that they should do. If we implement it in open source, then everyone gets upset. So the particular question was about the S3 DistCP, wasn't it?
And I guess EMRFS too.
Okay, so the EMRFS, they've put a lot of work in actually stuff that we will be doing, hopefully mimicking in CGuard. Interestingly enough, the CGuard stuff, the use of DynamoDB as your reference index, was actually implemented first by Netflix. So Netflix actually added it on top of Amazon's EMR S3 client using, I think it was Mockito or Mock4j, one of the mocking libraries to patch the Amazon code. So our implementation, we're looking more at Netflix's work than Amazon's direct. As far as the DistCP work goes, we have been improving some of the bits of the pure Apache S3. So the pure Apache DistCP to work a bit better with object stores is where we're looking at right now.
Thank you.
I have a question regarding the pricing of DynamoDB.
What was the sorry?
Regarding the pricing of DynamoDB. So DynamoDB, it charges based on read and write a request, right? Request per second. So what would be the additional cost for a customer who moves on to a new output committer? Right,
that's a good question. So the thing about DynamoDB is it doesn't actually change you per read or per write. It charges you per provisioned read or write. So it says, right, I want 25 reads a second. Then that's how much it's going to cost you. If you want 25,000 reads a second, it's going to cost you a lot more. If you overrun, I've got 40 seconds before drinks begin, by the way. Sorry, I'll be fast. Essentially, we're going to put throttling in there with throttle detection. So if you under-provision what you want, you're going to basically get throttled. We'll retry, and our performance metrics will be counting, saying, hey, hang on a minute, you got throttled a bit, so you can maybe tune it low. I do not know about the actual pricing, though. That's the main thing I have to say. I'm sorry, don't know that answer.
Just a follow-up question, quick one. Did you guys think about using manifest files in some persistent store for the output committer? What were the trade-offs when compared to DynamoDB option?
Define manifest files.
A file containing list of entries in S3, for example.
Okay, in that case, effectively, the information we save for a pending commit is saved to a file, and that's how we share it between the different nodes. The problem is that we need that consistent on listing. I need to be able to list a directory tree and find all files pending to be committed. Without a consistent list operation, we cannot do that. And with that, I'm afraid, time is up, and the bar is open.
All right, everyone, round of applause for Steve here.